I am continuing to look at things tipping over, and I'm going to make a video, and I'll probably stop for a little bit after this and do some other things because, I have other things I need to try to make videos on also. But I've been making videos to model something like this, a stick that just tips over. Okay, and let me just show you where I've been. The playlist for all this is down below, so you can go back and look at this. This is your first time thinking about it. And so I like to model things in multiple ways just for comparison, and then each model does something a little bit different. So in this first model, I had the stick as though one end was fixed and the other end could rotate. And I have, in all these cases, I just have two masses connected by a massless string, a massless stick. I'm sorry, it's a stick. So in this model, I have the angle, the tilting angle theta, and I just use the torque on this system, on the mass actually, because that's fixed, is equal to I times the angular acceleration, where I is the moment of inertia. And then once I find the angular acceleration from this, then I can use that to update the angular velocity and use that to update the angular position, and this works pretty well. In my next video, I did the same problem, but instead of using angular momentum and torque, I used just forces. And the problem here is this constraint force from the stick is difficult to calculate, so I didn't. Instead, I replaced that stick with a spring, a very stiff spring. And so this stiff spring, if you move this mass down a little bit, then that will compress the spring will push back that way, and then you can just say there's two forces on this mass, the spring force due to the position of the mass and the gravitational force. And you actually get the same answer over here if you have a small enough time interval. It's close enough that you wouldn't notice the difference. So this just uses the net force is a change in momentum. I can update the momentum in each time interval, but I need to calculate the force each time, which is the gravitational force plus the spring force, which depends on the vector length between these two and the spring constant. And that's that. And so I did that one. After that, I went over here and I looked at the situation where the pivot is no longer fixed. So now I have two masses, and I originally did them as equal masses and I made a mistake. So I redid it as a punishment, I redid it with unequal masses so that you could change, which is a good idea. So now I have two masses, both of those can move. So this is like if this is the ground, I use this pencil as the ground, and here's my stick. This one with the two masses, it doesn't just tip over. It tips over and it can slide. So in that case, I used Lagrangian mechanics. So Lagrangian is kinetic energy minus potential, and this is the Euler-Lagrange equation for the theta angle. I also have to do it for the x, and then I modeled that. After I got the differential equations, I then used the Euler method to do that. And I think that worked pretty well, and it's a really great mechanics problem. And there is another way to do that, but I like to do it Lagrangian because I like Lagrangian mechanics. So finally, here we are. I want to repeat this experiment with the two moving masses, but instead of doing Lagrangian, use a spring between those two. And so I'm actually going to use two programs I already wrote, so I'm not going to remake them. I'm going to use this one, which I already have, and it's not going to be, I don't think, too difficult to change to make it like this. And then I'm going to compare the values with this right here. Okay, so let me just remind you how I'm going to do that. The first thing is the spring force, right? So the spring force is some constant, spring constant. And then what I'm going to do is, suppose I have two masses. Let me just redraw my masses right here. There is an unstretched length L0. And that is, when they're L0 apart, there is no force. So the first thing I'm going to do, let's call this mass 1, this mass 2. I need to calculate this vector L. So vector L is going to be equal to, let's say that's R2 minus R1, where so this could be my origin, and this is R1, the position, and this is R2, the position of that. So the vector from 1 to 2 would be R2 minus R1. Then I can take the magnitude of that, and I get the following. Fs vector negative k times the amount it's stretched or compressed. So I'm going to write that as the magnitude of L minus L0. I can't do L minus L0 because L is a vector. But then this is going to be just a scalar value, and I want a vector value because this is going to change directions. So I need to multiply this by L hat, where it's just a unit vector in the direction of L. Now this will give me the force on this mass up here, and I already did that. But now I need to do it also for this force down here. So this mass down here is a little tricky. First of all, the force down here is just going to be the opposite of this force. If this is a massless spring, the amount the spring pushes on mass 2 is equal and opposite to the mass on 1. Now I do want to make sure this mass doesn't fall through the floor. So what I can do is just use this to, I'm not actually sure how I'm going to do it. I can just say, okay, set the position. I think I might just set the position equal to the same position all the time after each iteration. But that should be it. I mean, I can just take that program right here and just add that force in here and make sure this mass doesn't move to the floor, and it should work. And then I can tip it over and compare it to this. After that, I'm going to add friction. So let me just say what I'm going to do to add friction. So the frictional force, I can model the magnitude of a kinetic friction force as some coefficient of kinetic friction times the normal force. And it would be in the x direction. So I'll just multiply that as x hat. So I'm going to need to determine the direction of this frictional force because it could be in the positive or the negative x direction. And I'm going to need to determine the normal force. So let's draw this mass. Let me draw it on another picture at the bottom. So here's my floor. Here's my mass. And so what forces do I have on there? Well, I have the downward gravitational force. Am I calling that M1? I think I'm calling that M1. I messed this up a couple times. M1. And then I have the spring force like this, Fs. And then I have the normal force like that. And then if this is getting pushed this way, the friction force would be this way, F friction. So I need to find that normal force. So here's what I could do. In the y direction, I don't want to, I could model this as another spring and say, oh, it's just getting pushed into the floor, and just calculate that spring force into the floor. But I don't want to do that. The magnitude of the normal force, I'm going to say F net y is going to be equal to N minus, this is M1G, minus M1G, right? That's the gravitational force. And then I need the y component of the spring force, minus Fs y. That's the y component of the spring force. And that should equal 0. Because this is not accelerating in the vertical direction, that has to be true. So I can actually solve for n. N equals m1g plus fsy. So I can get the y component of that spring force and then use that to find the normal force, and then write the frictional force as a vector. It's going to be equal to, I think I'm just going to call it positive and not worry about it. Technically, it'd have to I know I can do it. It's going to resist the motion. So let's actually put this correctly. So it's going to be mu k times n, the scalar, 0, 0. And then I'm going to multiply it by negative p1 hat. So if this p1 is the momentum of mass 1, if it's moving this way, then the friction force is going to be that way. If it's moving this way, the friction force is that way. So that gives me the direction and then the negative. Okay, I think I'm ready to jump into Python. Let's see if we can get this thing to work. Okay, what do I have over here? Okay, so this is my spring, my mass with a pivot. So this one does not have both masses moving. Let's just run this. Let me go over that. Okay, so I'm gonna get rid of that falling ball. Let's do that, and let's call, which I should do this anyway. Let's change pivot to ball 1. Ball 1. That's fine. Ball 2. Is that the one that drops? Yeah. So let's get rid of that. I don't want that at all. No ball 2. This is going to be ball 2. So ball 1 is the one on the bottom, and then ball is the other one. I know that's dumb, and I'm a terrible person for doing that, but that is what it is. So ball 1.pos. That's fine. This is going to be ball 1.pos. This is going to be ball1.pos. G is fine. Ball2.v. That is the initial. I need ball2.p. Ball2.v. Okay, let's do ball2.p equals equals. Okay. Oh. No, I got rid of ball2. So I have ball1 and ball. So let's say I'm going to go up here and say M1. I'm going to use M1 and M2 instead of putting it as a property just because it's easier to see. So then I'm going to say ball1.p equals M1 times vector 0, 0, 0. That's the initial momentum. I need that. And then this is going to be equal to M2. Oh, let's put this both to 1. Okay, so then I have the, and that's that. Okay, good. T, that's good. While ball.pos, that is greater than ball1. That's a little weird because ball1 technically could move, but I'm going to try to make it not move. So let's just leave it like that. And then this changes to ball1. Ball.p. Stick, move the stick. Okay, I am going to need to do something else too. Ball1.pos. I need to move the location of the stick. So I'm going to say stick.pos equals ball1.pos. I need to attach it to that. It's going to move. Ball2, I don't need that. I don't need that. I don't need that. I don't need that. Don't need that. Okay. So this should be the same. The only thing I did was change the name of pivot to ball1, and I got rid of ball2. So let's, and I did copy this. I did copy this, right? Okay. So let's call this, let me run this. Okay, so it is working. That's, I guess, what I would expect. Why is it shake? Was it shaking that much before? Okay, let's see. So this is called tipping stick spring with 2 masses. Does that sound okay? Okay, so I think all I need to do now is to go down here. Fnet. Here is, let's call this F spring. Fs equals, I'm going to cut this. And then put Fs. Okay, so all I did was move that up there. And that's the force on the top ball. I need to do the same thing for the bottom ball. Let's update the momentum of the bottom ball. So, ball, can I just do it in the X direction and say the Y momentum doesn't change? I'm going to try that. Ball1.p.x equals F negative Fs.x. That's the X component of that. Plus, no, it should be like this. Ball1.p.x plus, no, minus Fs.x times dt. So that's just the X component of the momentum principle for ball 1. I don't care about the Y component. I'm not going to change the Y component. And now let's do the same thing for the position of ball 1. Ball1.pos.x equals ball1.pos.x plus ball1.p.x times dt divided by m1. Okay, so that should do it. That should do it. Okay, so they're the equal masses, so I should see them both move. Okay, now let me change this because that's too small. I want to make that ball 1 0.5. There, that looks better. It looks good, but I get a tipping time of 6 seconds. Okay, so let's see. So K is, what did I have for K? Was my K too small? K is 1,000. I think that's fine. It seems like if I go over here, this is my Lagrangian one. If I run this, equal masses, 0.7. So 0.7. So this one runs And see, it looks like it's not landing in the middle too. Let's print, I could print the center mass, but let's just do this. Print ball1.pos.x, and let's print, no, let's calculate the center mass. rcom equals ball1.pos times m1 plus ball2.pos times m2, all of that divided by m1 plus m2. And let's print that. At the end, it should be the same as before. That's the center mass, rcom, and it'd be technically in meters. Okay. Ball 1, ball 2. It didn't print it out. Oh, that's why it stopped. Okay, so something's going on here. I had an error. Ball can't find variable ball 2. Oh, that's in the printing. I think that's just here. That's just ball. Ball 2 is ball. Okay, so the center mass in the x direction is 0.17, so it did move a little bit too much to the right. Let's see, where does it start? Oh, it didn't start. I should print it up. I should do the same thing up here. Let's calculate this before they fall. Let's do it up here. Because it's not, doesn't start at x equals 0. Okay, so it's fine. It did work. But it took too long. It didn't take long enough. Let's try one thing, and then I'm going to move on. Let's just make the time step smaller. That is could be part of the problem. No, 0.06. Is my length the same? Length is 1. I'm not sure why I'm getting a different value. It looks like it's working, but I'm not sure why I'm getting a different value from over here. That has mass 1 and mass 2 is M1 and M2, both 1. And this is 1 and 1. Let's just change this to M1 is 2. Let's just want to change 2 and run it and see what I get. 0.81 seconds. And if I change this one to 2, I change M1 to 2. Do I increase in time? It did increase in time. Okay. Well, I'm not 100% sure there, but I do want to add the friction. So let's add a frictional force. Oh, let's do this. Let me test this. If M1 is 2 and this is 0.1, or let's make this one even 3, then it should go back to the normal, close to the one where the lower mass was stationary, because that mass is so heavy. Okay, yeah. So I think it is working. I think it is working. I'm not sure why I'm getting a different number, though. That's something I'm going to look at. Okay, so let's go down here, and I'm going to make a coefficient of friction. Mu k equals 0.2. I'm just pick that. Okay. And then down here, when I calculate the momentum, when I update the momentum of ball 2, I'm only saying it has that gravitational force. But the first thing I need to do is calculate N. So N is going to be, now I'm looking at my formula over here. It's going to be M1 times the magnitude of G plus Fs dot Y. So actually I need to, the magnitude of that. So I need to do plus, so I just use this, Fs dot Y. I think I use that one because that one is in the positive direction, and that was the way I drew it. Well, when I solved it, I need the magnitude of that. Okay, so that's N. It's a scalar value. Now F friction is going to be equal to mu k times N times the norm It's going to be negative over here. Negative norm ball1.p ball1.p, which is moving in the x direction. And I think, yeah, because I only allow that to move in the x direction. Now, the problem is on the first step, the ball's not moving. And so there's no friction. So I think it'll move at first, and there won't be friction until it moves. No, there would be. Well, ball1.p is 0. Yeah, which is fine because let's run it. Oh, and then I need to go down here and say this plus ff.x. That was all in the x direction. If this works, I'm going to be pretty impressed with myself and pretty happy. Okay, so it did take less time to fall over. I think I have a negative sign problem. And it went, yeah, because it moved, the center mass moved to the left. So let's just go over here, and I'm pretty sure that's all my problem is. I'm going to change this. Just get rid of this negative sign. Yep. Yep. And that's pretty good. I'm pretty happy with that. Let's make that very low friction, 0.02, and then it should be very close to the way it was before. Yep. And then with high friction, the pivot's basically stationary. So I think that's working now. I'm pretty happy with that. I think there's still some things I need to play around with this, but I'm going to leave that for homework or something for you to play with, because I'm going to take a break from this and finish my other projects. I'm going to come back, and what I want to do is to do not two masses, but a rigid object. And I have a couple ways I want to do that, because if it's a pencil, it's not two masses at the end, it's actually a rigid object. So it might be a couple weeks before I get back to that. I got to do some homework for my other classes and stuff, but the code for this is down below. The playlist of the other videos in this are down below, and hopefully you find that useful. That's that.